superconducting qubits. And the story I will tell you today is a bit more technical. So it's about also a bit visionary. So it's about the future where we have actually nearly perfect qubit and still want to control them with fast and high fidelity gates. So let's assume now we have a qubit which we can isolate very well from the environment, and it lives then forever. So that's somehow what we want. We want quantum information to be stored, but we cannot look at the quantum information because as soon as we look at it, we will project it. So we have to isolate it as much as possible from the environment. But on the other hand, we want to look at it at the end of our experiment. So we want to get the information out fast, and we want to also to control it. We want to do pi pulses and control it very well. And all this opens actually decoherence channels, so ways where the quantum information can leak out of your qubit and you lose information. And this talk will be about how to tackle actually this paradoxical challenge that you want to isolate it but read it out at the same time and control it at the same time. And also a short primer, so we've heard of Yuri, what we're working with is LC circuits. So yeah, we've manufactured them with superconductors because everything dissipative in our systems is actually looking at the quantum state. So we don't want dissipative elements, so we only have inductances, capacitances, and if you build a circuit out of it, we get an LC circuit which behaves like a harmonic oscillator. In our case, then the conjugate variables are charge and magnetic flux or magnetic field, and you can express it in branch fluxes, which is the second operator, this phi operator, and number of charges, which we call n. Okay, and then there's an element called the Josephson junction, and this was actually a huge success story for theory. So we've heard in the nice quantum Stammtisch yesterday that there's this thing that, for example, theorists and experimentalists are in the lab together and suffer together. And here it was actually that they suffered together in a lecture, and they describe it more like they enjoyed the lecture together and had this brilliant idea by Brian Josephson that you can actually tunnel Cooper pairs, so electron in pairs, through an insulating area. So two superconductors separated by an insulator. And you can get a tunneling current through this. And this behaves actually, in our case, like a nonlinear inductor. So the more electrons you tunnel through, the higher the inductance of this element becomes. And yeah, this was then predicted in this lecture. They had this idea written up by Brian Josephson, published, and he got the Nobel Prize for it. But surprisingly, Phil Anderson was sitting next to him in the lecture and did the experimental verification directly at the same year at the Bell Labs. So this was also somehow a huge success story with sitting together and developing these ideas. Okay, now if we have this element, we can actually build nonlinear LC circuits. So just by replacing now the inductance with the Josephson junction, we get an element which is already nonlinear enough that with a single quantum of excitation, we change the resonance frequency of the system and therefore have quantum control of our system. The Hamiltonian now changes from the harmonic part, so from the parabola to a cosine potential, and this gives us the nonlinearity. Okay, good. That's our toolbox. In reality, it looks like this. So the most simplest circuit we can build out of this is called a transmon. So this is just the two capacitive pads, so which you see here, which are extremely microscopic. And in the middle, we place the two superconductors, let it oxidize. So pattern a lower aluminum superconductor, let it oxidize, and pattern another superconductor on top of it, which gives us the Josephson junction. Okay, so then we need the two elements. One is readout, and with this we couple another LC circuit to our qubit. And we can couple them very strong that we can actually get a dispersive coupling where the resonance frequency of our coupled LC oscillator depends on the qubit state. And with this, we actually have now a tool of really a Q&D measurement of the qubit. So just by probing the resonance frequency, for example, with a fixed tone, and see if there's no transmission or high transmission, we can detect if the qubit is in a ground state or excited state. And yeah, we can do this with amplitude, but we can also do it with phase. So what you see in here is the in-phase and out-of-phase component, what we typically measure. But what you see is that actually we can do it with a single shot, so a single pulse. Measuring the system is a single point here, and we get already the full information. So on the bottom, you see actually a cut now through the q equals 0 axis, and you see that if we detect a high number or a high voltage, we can say it's an excited state. If it's low voltage, we can say the qubit is in a ground state. And this is actually also a very QD measurement. So if we do the same measurement twice, we will detect with high probability the same measurement result. And this is important for also state preparation protocols where you measure and then you want to make sure that the qubit is in the state you want to be it after your preparation. And also a strength here is that we can do this very efficiently. So yeah, for the experts, we get a measurement efficiency of 20%. That means 20% of the photons we send in, we also detect and can actually infer the information of the qubit out of it. Okay, the other ingredient we need is control. So for this, we just add another channel capacitively coupled to the qubit. And here we just send microwave pulses at the qubit frequency. And yeah, for example, by fixing the pulse length and just sweeping the amplitude of this pulse, we can then see Rabi oscillations, what you see here. And we can do arbitrary then single qubit oscillations on the Bloch sphere. So do pi pulses, pi half pulses, anything we need. And this we can do very fast, within 10 nanoseconds, and achieve gate errors below 10 to the minus 3. Yeah. Okay, this brings me to the state of the art, which we've heard in the talk before, are transmons. They are incredibly beautiful because of their simplicity. So you break it down to the really essential elements. You can optimize fab and optimize scaling. And where our whole field is now going to is actually towards fault-tolerant quantum computation. So we need really error correction. Yeah. People in the beginning in the 90s thought that quantum computation will never be possible, but it turned out with error correction we have a chance, and this is where we have to go now. But for this we need low error rates on physical qubits, and low means below a threshold which is given by the code you choose. For surface code it's typically around 1 or a little bit less than 1%. So we have to make sure that all of our operations, so readout, 2-qubit operations and single qubit operations are in some below 1%, so to benefit from quantum error correction. And that's what we have to do, and what was impressively demonstrated by Google last year that it's working. But if we look at the limitations of current processors, which is given summarized and also the paper by Google, you see that the main limitations for transmons are coming actually still from gate errors, leakage out of the computational subspace. It's still a very harmonic qubit. Crosstalk, so if you have a big processor, all the lines talk to neighboring qubits, and also the coherence of the qubits itself. So they live like 100 microseconds, or a bit less than 100 microseconds for the Google processor. So just idling gives them already an error. And for this coherence, so what limits actually the coherence of the qubits, we can separate it into these two channels. One are internal losses. Since we have this mesoscopic systems, we are really sensitive to defects on the surface, and it's really a hard task to get surfaces very clean, and that's where the whole community is now working on to get pristine surfaces, to get these defects away. And the other loss channel is actually external losses. So just by wiring, adding control channels, we also can lead the qubit to decohere. Okay, for tackling the first channels, the first challenge, the internal losses, people thought about different qubits. So there's a whole zoo also. That transmon is somehow the simplest element, but it's not really how it started. It started a bit with the QPaper box and then developed into phase qubits, flex qubits, pioneered by Hans Moy and also at the Walter Miles Institute. And then finally everyone settled for the transmon because it seemed to be the best approach in terms of demanding for fabrication and also giving high coherence. So there was a famous plot similar to the Moore's law given by Michel Devray and Rob Schulkopf, which showed that actually in the beginning years of our field, also the coherence time or the lifetime of the qubit was exponentially rising, but somehow this now settled. So this was 2013, but now 10, 12 years later, we are still at this plateau, so at around 100 to microseconds to maybe, if you have really good qubits, to a millisecond. And there, another qubit now turned out recently, which showed high coherence and also high gate fidelities, which is called the fluxonium. So compared to your transmon, you add now a new element, an inductance in parallel to your structure. But you can also be becoming more and more creative. So you have these elements, you can combine them, and you can build very complex circuits out of it, which bring you maybe intrinsic protection, so that you can engineer your matrix dipole elements, so that in your computational subspace of 0 and 1, you don't have any dipole moment driving these transitions by getting complex circuits. And then you have to just to think about if you can fabricate this well enough, so if it meets the experimental or the reality, and then you have to think about how to control it, because if there's no dipole moment, you have to think about other ways, and maybe the ideas we are bringing here are also useful for controlling these systems. But in the remaining talk, I will now focus on the fluxonium, because it brings some benefits. And yeah, these are the people at the Walter Meister Institute working on fluxonium qubits. Similar to a transmon, we can control it with, or read it out with a coupled LC oscillator. We can couple a control line and use all the technology and know-how we built up for transmons to control these circuits. The heart of the fluxonium is compared to the transmon, which are really just the pads in the junction. Now this loop here in the center, where we have a very high inductance, which is built out of an array of chosen junction to get these high values, and a single junction. So this is really the heart of the fluxonium in this case. And if you do this and apply a magnetic flux of half a flux quanta in this loop, you get a potential that looks very different to the nearly parabolic potential of transmon. So you get this double weld potential. And here we encode the qubit in the lowest two states, so the 0 and 1, and these are close together, typically now in the range of 400 megahertz to maybe 1.5 gigahertz, or even going lower. So people also manufactured fluxoniums with 90 megahertz transition frequencies. And the nice thing is now that the higher levels are much higher. So it has a huge anharmonicity. So leakage out of a computational subspace becomes harder. So if you make pulses short, which become spectrally broad, it's now less likely to go to these higher states. We now have first working fluxoniums at the Walter Meister Institute, where we're quite happy, with decent coherence times around 200 microseconds. So we can really work with this. And what speaks for fluxoniums is, people have demonstrated record-breaking single qubit operations, 2 qubit operations. Record coherence times was also still valid for fluxoniums, around a millisecond. You can play around a bit. You have this additional flux tuning knob, so maybe it gives you some additional protection. The biggest benefit we see actually right now is going to lower frequencies, we have lost crosstalk on bigger QPUs, and that's what we are betting on. We also gain less leakage to the higher states. If you compare the size, it looks also a bit smaller than transmons or long-lived transmons, so you can also shrink down transmons a bit, but fluxoniums offer also the potential to go a bit more compact, so all this offers advantages for if you think about QPUs. What speaks against it is actually that it's a bit more demanding for fabrication. So instead of a single Joseon junction, we now need order of 100 Joseon junction for a single qubit. So if you now make a QPU out of 100 qubits, so this quickly explodes. So you have to have very reliable fabrication. And we also add another noise channel, so we now have a closed loop where flux can thread through, so we make us more sensitive to magnetic flux. And the biggest challenge is actually that no one has demonstrated a scalable architecture. So people made strings out of it, but for surface code where we want to go, we really need a lattice out of it, and this has not been shown yet. Okay, so this brings me to the main story of the talk is how can we control actually a qubit, so in the future if it's really very long-lived, and don't pay by adding now the control channels. So it's about this story, about the write. And specifically, I am focusing now on the control channel. So for the readout, we also have ideas how to eliminate this channel, but this talk will be about the control channel, so where we drive actually XY control of the qubit to pi pulses. And to make this the dominant noise channel, we actually now apply artificially noise on this control line to really make sure that this is now the channel we investigate and make sure that this is really the dominating noise or loss channel of our qubit. And if we do this, we now see that the T1 times and T2 times drop from, so this is the same qubit I showed you before with around 200 microsecond intrinsic T1 and T2 times. It drops now to 30 and 20 microseconds of T1 and T2. And to explain this, we can just look at Fermi's golden rule, where somehow the decay rate is given by the matrix dipole moment, that matrix dipole element, which we did not change. But also by the environment, so the noise density of the environment, which we know changed a lot. And in circuit language, we can actually describe it like this, where in the brackets, the first term describes the spontaneous emission of the qubit into this line, and the second term is about the stimulated emission. And you see now, since we increased the temperature of the resistor on this line, we now increase the second factor a lot, so we increased the decay rate of the system. But now looking at what is in front of the bracket, we can actually use this, because this is a parameter we can engineer and adjust. So, and this will directly change the spontaneous and stimulated emission. And this is called what is also called Purcell filtering or Purcell effect, which was intrinsically shown by Purcell to enhance actually the coupling to a qubit just by putting it in a cavity or an atom in a cavity and actually using now the inverse, what we are doing, enhancing the mode density. What we're doing here now is decreasing it. So making sure that the qubit cannot decay. And this we do by a low-pass filter, which now actually reduces this prefactor. So we have a passband much below the qubit frequency, which we need to apply actually the magnetic field for optimal operation point. But at the qubit frequency, it filters away. And if we do this, we can actually recover the good intrinsic performance of our qubit and are back to the 200 microseconds T1 time. So this is good. Now we have actually eliminated this decay channel of our control. But if we look at it now, we also eliminated our possibility to control through this channel because we cannot send pulses at the qubit frequency anymore because they are filtered. And to solve this issue, we are actually using the intrinsic non-linearity of our qubit itself. So as we found out, the pioneers of our field already used this technology to drive qubits is by going to fractions of the qubit frequency itself and using multi-photon processes. So instead of exciting the qubit with a single photon at the qubit frequency, we use now 3 photons at 1/3 of the qubit frequency to do to excite the qubit. And this was shown also, or had a revival recently for transons, and we thought that this should also work actually for fluxoniums, maybe even better. And this was also one of the stories where we thought a bit, we simulated a bit, we went to the lab and we had the sample and we tried it out and it directly worked beautifully. So what you see here is somehow on the y-axis the response of the qubit. If it's initialized in a thermal state, the y-axis or peaks on the y-axis will tell you that it's now actually rotating or changing its thermal state. And okay, if we don't use a filter, you see we can drive the qubit at its qubit frequency, what is expected. But if we add a filter now and going to lower frequencies, we also see the qubit response at around 1/3 and so on of the qubit frequency, and we can actually drive the qubit. So, but it's not really exactly where we would expect it, so it's a bit higher. And to understand this, we experimentalists, we have tuning knobs, we can actually tune now the amplitude of our drive pulses, and this is what you see here. So on this plot, on the x-axis, I sweep the amplitude of the drive pulse. On the y-axis, you see the frequency again for the low frequency scale. And what you see in color is also, again, the response of the qubit. And you see, actually, there's a lot of things happening. So yeah, we were not sure what exactly is happening, so we just looked at the Hamiltonian and did a time evolution brute force just by diagonalizing it and looking at it and driving it at a fraction of the qubit frequency. And what we expect from numerical simulations are actually these lines. So we can now identify these lines here as the sub-harmonic driving, what we're interested in. And all the rest of the stuff is actually what I mentioned before. You see defects on the surface. So we shift our qubit frequency slightly, we couple to one of these defects, and this will actually also excite and change the qubit state. Okay, but what we also saw is that we still have a deviation. So now in red you see what we expect from numerical simulations, but on the experimental data we saw actually still a deviation. And to understand this and what's going on, we actually thought about can we get understanding? And this was a nice project by Longxiang in collaboration with Peter Rabi, who is also now at the Walter Mainz Institute. And it's really nice that you have directly this theory support and people you can talk to. And they developed a model which can actually describe now the frequency shift, or by increasing power, how the qubit frequency actually effectively changes. And they came up with a model or a formula which can describe this shift, which depends on the number of photon processes. So in this case, it's shown for n equals 3. And you see that it depends on the matrix dipole moment, matrix elements of the G to the E state and E to the F state, and then on the drive amplitude squared. So you somehow get a parabola with increasing amplitude. So we can actually model this. And also interestingly, it depends on these two matrix elements. And if you set in the numbers for transmons, this is actually just square root 2. So if you square it, it's 2. So this cancels out. So for transmon, this disappears, but for fluxonium, it appeared. So for more nonlinear systems, actually, you will get more of this drive shift. And it also appears for the Rabi frequency. And it turned out that for more nonlinear qubits, like the fluxonium, it's working even better, the sub-harmonic driving. But if you now plot it and compare it to simulations and data, you see that it actually agrees very well to simulations, what you also naively would expect. So there must be another deviation to the experiments. And there we again looked at our setup. And one thing we realized is actually that we are using very thin coaxial wires, which could lead to distortions, and we calibrated this or characterized this. So on here you see actually on the x-axis the time scale, on the y-axis an amplitude of a flux pulse, so a change in qubit frequency we want to see at the qubit. And we saw that we apply this pulse, but you see that it's a bit distorted. So in blue you see the data, how the qubit actually responds. And these distortions come actually from losses in the thin coaxial cables. Specifically, it's the skin effect, so which gives you a frequency-dependent loss channel. And you can model this with a simple model where you say, okay, you have your drive strength at DC, but it will scale with the square root of the frequency for higher frequencies. And now if we include this model and compare now our simulations and model to data, and we fit it so with this one free parameter, this A naught here, that we get good agreement. So now you see actually it's aligning well. We can now predict what actually the loss at 1 gigahertz, for example, is by fitting this parameter, and we can compare it to what we measure with the VNA and also what is given by the manufacturers for all the elements we have, and we see that it agrees very well. So we are quite optimistic that this really explains the difference. And for the rest of the talk, I will now fix this number due to this measurement for all residual measurements. So there's no free parameter anymore in the model, and we get good agreement only by using this single free parameter, which is also really nice. Okay, but what we're then really interested in is, we want to do computation. So we want to do gates on the fluxoniums. And to do this, we have to show 2 minutes, okay, Rabi oscillations. And so we saw that actually for n equals 3, we saw nice Rabi oscillations, and they scale actually with amplitude, and also similar to what we expect from naively multi-photon processes. But the nice thing is now we could go higher, so it means lower and lower frequency, 1/5 or 1/7, 1/11 of the frequency, and we can still see nice Rabi oscillations, so with 11 order processes. We also saw that naively, you would not expect to drive them because you would think they need so much power, but somehow for these systems works very well because they have a smaller power dependence like you would naively expect, which is also coming out of the theory. And okay, what we then, the gold standard for quantum computation, what we have to benchmark is actually gate performance. So now do multiple gates, apply them, and see how this performs. And we do this with some kind of amplification scheme, which is called randomized benchmarking, where we play just a random sequence of Clifford operations, which bring you on the cardinal points of your Bloch sphere. The nice thing is that smart people, Gottesman, have showed that if you stay in this subspace, you can compute it efficiently classically, so you can find the inverse of all these elements efficiently, so you can undo it in the end and always get the same result, and now compare to what you get to what you expect, and get a fidelity now on your sequence of elements, of randomized elements. And we see if we don't have a low-pass filter, we get a gate fidelity of 99.87. If we now add the low-pass filter and drive sub-harmonically, we get an improvement to 99.9 fidelity. But to have a fair comparison, because we saw that actually the coherence improved by adding this filter, we added another line just to show that how sub-harmonic driving compares to resonant, so the classical way of driving it. And we see that we still have a bit worse, but we are getting very close because this is coherence limited. So yeah, we are optimistic that actually with optimal control we can reach the same. So with this, actually, I now showed you that we can get high fidelity qubit control, which is on par or very close to resonant control through this single Purcell protected control channel, so which really opens an avenue for scalable quantum compute QPUs. Yeah, I also hopefully showed you that fluxoniums could be a worthy successor of transmons. And yeah, so where our story brings us, or where we want to go, is actually we want to build a QPU with fluxonium qubits. So now replacing, so using fluxoniums as a drop-in replacement for transmons. And the next big step would be actually to demonstrate now this connectivity for that one fluxonium is connected to 4 neighboring fluxoniums, and this is what we want to do in the near future, and then also somehow branch into them or build larger QPUs with fluxoniums. Okay, and with this I want to thank you for your attention and show you the people who are actually working on this. Thank you.
Yeah, thank you, Christian, for the great improvement in qubit control. I'm sure that there are questions now. Okay.
There are 2 issues. One is that so we don't want galvanic coupling, because for QPUs, if you connect everything to everything on big chips, you are very sensitive to magnetic fields, and this is an issue. So we want to have capacitive coupling. But unfortunately, fluxoniums don't have much capacitance to share. So if you now have a pad and want to share 4 neighboring fluxoniums to it, you don't have enough capacitance to get strong coupling to each one. So you get a very weak coupling, which decreases in the gate speed. You can think about other gate schemes, but then you have typically, so MIT showed a really nice gate, but there you lose a bit in frequency crowding. So to drive now transitions between neighboring qubits, you have many levels which you have to drive, which are very close. So you cannot make the gates very fast, because then you would have actually spectrally broad. So you would also drive transitions to other qubits which you don't want to drive. So these are the 2 main challenges you have to address for fluxoniums.
Yeah, next question.
Yeah, thank you very much. It seems that generally speaking, going to lower frequencies means you become slower. And that doesn't seem to bother you much here. Can you say why?
So slower means because you're frightened that for your rotating wave approximation that you go a bit strange up on your Bloch sphere. But it's not really true. So you can play some tricks with pulse schemes where they even could show for this 90 megahertz fluxoniums that they can do gates in 100 nanoseconds or faster. So this is not really a big challenge for gates, I would say. So there are tricks around it. We can discuss it, but yeah, it's not an issue. The more issue is that it's lower in frequency, is that it's again technical. In our cryostat, we only reach 20 millikelvin, so the thermal state of the qubit is then more likely, it's very excited, so you have to get a good reset protocol that you get from this thermal state back to 0 or ground state, and we do this with active feedback. So we just measure the qubit and then do a conditional pi pulse on our measurement result.
Okay, is there another question to Christian? No? Then let's thank him again.